Let's proceed to the next example. Sand is being dropped onto a conical pile in such a way that the height of the pile is always twice the base radius. Find the rate of change of the volume of the pile with respect to the radius when the height of the pile is at 4 meters and 8 meters. So let's have sand. Suppose this is the conical pile. And you have here sand dropping. Alright. Now we're given the relationship that, oh, this looks like a mountain, that the pile's height. Alright, we have here the height is twice the base radius, which is 2r. Meaning to say, we can get the ideal shape, that of a right circular cone. And we have a certain radius. We have here r. And so we need to know the rate of change of the volume. Recalling the volume of a right circular cone is 1/3 of the area of this circular base times its height. So we need to express height in terms of radius. So volume is equal to 1/3 pi r squared times height is twice the radius. So volume is equal to 2/3 pi r cube. And so finding the derivative, dv dr is equal to 2/3 pi times derivative of r cubed, we have 3r squared. dv dr is equal to 2 pi r squared. Substitute values for r, or the radius. Let's have dv dr is equal to 2 times 4 squared, that is 2 times 16, that is 32 pi. So units in cubic meter per meter. This is letter A. This time, let's have when the radius, sorry, I have it wrong. Apologies. Going back. So the height of the pile is 4. Okay, we have to express. So this should be, if this is the height, then the radius for A should be half of the height. So this will be 2 meters. And for B, this will be 4 meters. And so for letter A, this will be, so 2 pi times 2 squared, so that is 8 pi cubic meter per meter. And for letter B, the derivative is equal to, or rate of change of the volume, that will be 2 pi times, so that 16, that's already, this one is 32 pi cubic meter per meter. So this is for letter B. Alright. So apologies. So always be mindful of the given dimensions. Always be careful to see to it which it refers to. So let's have our other example. Alright. So this time, we have here a rectangle. The length of a rectangle is 4 inches more than its width, and the 4-inch difference is maintained as the rectangle increases in size. What is the instantaneous rate of change of the area with respect to its width when the length is 12 inches? Let's draw your rectangle. Suppose this is rectangle. So the length, we know that the length is said to be 4 inches more than its width. Alright. And so we know that we need to find the rate of change of the area. Okay. So let's try to illustrate the rectangle first. So for example, this is the rectangle. It means that our length is greater than the width. Alright, there. We need to know dAdW. Our independent variable is width. So we know that area is length times the width, and length is 4 plus W. So we can express area in terms of width. 4 plus W times W. This will be equal to, area is equal to 4W plus W squared, or W squared plus 4W. We need to know dAdW. So the rate of change of the area with respect to the width is equal to 4 plus 2W. So we need to know what will this be when the length is 12 inches. Now when the length is 12 inches, going back to our first equation. And so if length is 12 inches, therefore the width is equal to 12 minus 4, and that will be 8 inches. So substitute 8 here. Therefore, the rate of change, instantaneous rate of change of the area with respect to the width is equal to 4 plus 2 times 8. So this will be 4 plus 16, that is 20 square inches per inch. So this is our final answer.